Okay, so the plan is to consider probability, right? Okay, so just to start with, right? We know that the word probability, okay, is a frequently used word in everyday conversations. Okay, we can say, for example, it probably will rain tomorrow, or that person is probably guilty of the offense, or the bus will probably be late. Okay, so what does the word probable here mean? So, I mean, in the past, we've had a number of philosophers adduce different kinds of meanings to the word probability or probable for that matter, right? So, if you study the philosophy of mathematics, you come across people like Thomasius, okay, who said that the word probably is essentially a concept which lies midway between truth and error. All right. So if you say that the bus will probably be late, we're not saying that as a matter of certainty the bus will be late. Okay. We're just saying that we don't know whether it will be late for sure or it would arrive early, but it has to be somewhere in between. Okay. And we characterize that sense of in-betweenness or that midwayness by using the word probable, right, or probability. Then you also have philosophers like Remiers, okay, who has indicated that the word probable is more or less an assertion of which the contrary is not completely self-contradictory or impossible. All right. So when you say that he or she is probably guilty of the offense, we're here at this point just indicating that if you take the contrary, that the person is not guilty of the offense, that in itself corroborates the earlier assertion that we made. All right. Because saying that he is probably guilty of the offense and also saying that he is probably not guilty of the offense is somehow equivalent. Okay. Because in both regards, there is a measure of a midwayness between the truth and the falsity. All right. Then, of course, you can also talk about Kant, right, who has indicated that when we talk about probables or probability, it is sort of that which, if it were held as truth, would be more half certain. Okay, it will be more than half certain. So he sort of notched the interpretation a bit further by adding a sense of measure to it. Okay. In other words, he's just saying that when you say that something is probable, it means that it is more than it's more likely to be the case than it is not. All right. And so when I say that the bus will arrive late, it just doesn't mean that I don't know that the bus will arrive late or it will arrive early. By the very statement that the bus will arrive late, it means that it is more likely that the bus will arrive late than it would arrive early. Okay, so Kent is suggesting that probables, or in this case, probability, is that which, if it were held as truth, then it will be more than half certain. All right. But of course, this class is not a class on philosophy, right? So we shall not concern ourselves with philosophical definitions, but I'm kind of throwing this out there to get you to appreciate the fact that all of the mathematical nuances have very critical philosophical underpinnings, okay, that kind of makes them what they have become today. So many of the things that we'll be studying were very abstract concepts that philosophers of the past brooded over, okay, because in the past, philosophy and mathematics were very much had a lot of mutuality, okay. But of course, over time, they grew apart and they became more and more distinct disciplines. So some phenomena can give different results, okay, when repeated trials, when experiments are performed. And we've talked about experiment, trials, different kinds of outcomes, et cetera, et cetera. So, for example, if a die is thrown into the air, the fact that it would come down is deterministic, okay? But the observation of, say, a six is uncertain or is non-deterministic, right? If we toss a coin, the fact that there will be an outcome is guaranteed. There has to be an outcome because once you toss the coin, it has to fall down. But as to whether it would be a head or a tail, we cannot really tell, okay? So that's the same argument that we're making for a die. When you toss a die, maybe you're playing a game or you roll a die. The fact that it would come down and give you a value ranging from 1 to 6 is deterministic. Deterministic meaning that we can know it ahead of time, okay? But what we cannot know, the part that is random, the part that is uncertain, the part that is non-deterministic is the particularity of the value. Is it going to be a 1, a 2, a 3, a 4, a 5, or a 6? There's no way that you can tell. All right. So the origin of the theory of probability goes back to the middle of, well, maybe the 17th century, okay? And it's connected to mathematicians like Fermat, Pascal, and several others, Bernoulli, Demoivre, Bayes, Chebyshev, and Gauss, and Kolmogorov, right? And some of these mathematicians have propounded very important theories that we will be considering in probability 1, probability 2, and then probability 3. And then, of course, when you get to your final year, you're studying probability theory, you'll be exposed further to some of these very important concepts. All right. So let's take a first formal definition. When we talk about the probability of events, okay, what exactly do we mean here? So let's take this first definition, okay. So we can say that the probability of a given event, okay, is an expression, okay, of the likelihood of occurrence of the event. Okay. Now, historically, there are three main schools of thoughts when it comes to defining and interpreting the probability of an event. Okay. And we'll be looking at that shortly. But basically, we have what we call the classical approach. We have the frequentist approach or the frequentist definition, and then the subjective approach. Okay, so the first two approaches, which is the classical and the frequentist approach, we call them the objective approaches, right? When we say a particular method or a particular approach of undertaking a task is objective, it simply means that it's not opinionated. It's not based on how what we think or how we feel about that particular event. Okay. The event is happening based on its own dynamics, which we cannot influence by the way that we interpret it. And then if we say subjective, subjective means that there's an element of opinion in there. It's not necessarily scientific. It's not a scientific or a factual assertion that we're making. The assertion that we're making about that particular view of the world is based on our perspective. Okay. So that's it with objective and subjective. Objective, we're talking about factual. Subjective, we're talking about not factual. Okay. So it has a sense of personal biases in there, so to speak. So the classical definition or the classical approach to defining probability is essentially a mathematical way of treating, or if you will, measuring uncertainty. Okay, as I talked about earlier, much of this theory was developed out of attempts or philosophical attempts, for that matter, to solve problems related to games of chance, such as rolling a dice, tossing coins, drawing cards, which used to be the order of the day, in times past. Okay, so it's based on the simple assumption that outcomes of a random experiment are equally likely. All right, and there is no reason to prefer any one of the possible outcomes to the other. As you move further on in your studies in probability, you'll get to appreciate that this argument is what we call the principle of insufficient reason. Okay, the principle of insufficient reason by Jacob Bernoulli. All right. Now, by this principle, all the possible outcomes of the sample space, either you call it an S or omega, should have the same weights or probabilities of occurring. All right. Such a finite probability space is usually what we call an equiprobable space. Okay, so let's take the second definition. So here we're looking at the approaches or the different schools of thoughts of appreciating probability. Okay, so I want to start talking about the classical perspective or the classical approach. All right, so let's take a definition. So classical. All right, so we can start by saying that if there are a possible outcomes, okay, favorable favorable to favorable to the occurrence of an event. And let's call that event caps A. All right. And B, and there are B possible. And there are B possible outcomes. Okay, unfavorable. Unfavorable to the occurrence of A. Okay. And at the same time, okay, all possible outcomes, whether A or B, all possible outcomes are equally likely. Okay, and at the same time, mutually exclusive. Then we can say that then the probability that event A, okay, will occur is giving as follows. So the probability of A is equal to A on A plus B, okay, which basically is what the number of favorable outcomes okay, on number of all possible outcomes. Okay. Now, most of you will recall this definition from sort of your pre-tertiary exposure to probability, okay? But this is probably the most basic way that you could appreciate probability, okay? As I talked about, there are three different schools of thought, and these different schools of thoughts would play out in your probability studies as far as your education is concerned, okay, in diverse regards. So I want to stress on the fact that this is one perspective. This is not the only way that you look at or you interpret probability. All right. There are other critical ways to look at it. But I'm starting with this because I know this is what most of you are familiar with. So I want to build on or from what you know. Okay. So we start with what you know, then we launch into some of the other schools of thoughts of probability that may be a bit more foreign to you. Okay, so we can say that equivalently, right? Equivalently, okay, equivalently, we can say that if a statistical if a statistical experiment if a statistical experiment, let's call it this, all right, can result in n n mutually exclusive and equally likely simple outcomes. Okay. And if A of the outcomes possess okay, let's say a particular attribute or characteristic or property, and let's call that A. All right. Then it holds. It holds that the probability of A, okay, is equal to A over N. Okay, so that's the core argument. So to explain how the classical probability expression, okay, this expression I mean, okay, to explain how this expression arises, let's suppose that our, so let me put it down. So to explain, all right, to explain how, okay, equation one arises, okay, suppose that the sample space, omega, all right, contains endpoints. All right. If the omega contains endpoints, then what is the probability of each point? Okay. Then we can argue that, okay, then the probability of each of the points, or in very simple terms, the probability of each point, okay, is 1 on n. Okay. So suppose also, So suppose also that the event A, all right, contains A points. All right. So now think about it. We are in the sample space omega, and there are n points in them. The membership, the size of the membership is n. Then we're saying that, of course, since they are all equally likely, okay, then the probability of observing one single point, is what? 1 on n. Now, if we further suppose, okay, that the event A contains some A points, all right, then the probability all right, of observing A, the probability of observing event A, okay, is the number of elements, okay, in event A multiplying what? The probability, okay, probability of each point. So probability of omega in omega. All right. And this is going to be what? So this implies that the probability of A is the number of elements in A is what? A. Multiply the probability of each member of the sample space, omega, is what? 1 on n. And this is what? A on n. All right. So this simply means that the probability of an event is the number of outcomes comprising the event as a proportion of the total number of equally likely outcomes in the sample space. Okay, so a quick example here. All right, so we can see that in a well shuffled deck of cards, all right, a card, right? In a well shuffled deck of cards, a card is selected at random. Okay, so the question is, what is the probability? What is the probability of A, a queen, B, a five, C, a spade, and then D, let's say a picture card, right? So you have we're in the context of a game of cards, right? And we know that a standard deck of cards contains 52 cards. And the reason why we're shuffling it is to create some randomness, right? So that at the time that we're selecting, there is no predetermination. In other words, we want to avoid or we want to minimize biases as much as possible, because then otherwise you might be predisposed to choosing, say, a queen or a five or a spade or a picture card, right? We want to be absolutely ignorant about what the outcome would be so that there is complete uncertainty in that regard. Then probability can properly be, can have its way, so to speak. All right. So we're saying that given the scenario, what is the probability that if we pick a card at random, we're going to get the following cards from A to D? Let's see how that plays out. So just based on what we saw, we realized that if you wanted to compute the probability of a particular event taking place, there are two things that we need to know. First of all, what is the number of elements in the sample space? Okay, the total number of possible outcomes. In other words, the cardinality of the omega, okay, the big omega. Then we would also want to know the number of favorable outcomes. In this case, if we're interested in the queen, how many queens are there in the first place? If we're interested in the five, how many fives are there in the first place? If we're interested in the spade or a picture card, respectively, how many are there in the deck? Okay, in the first place. So we can say that giving all right, giving the scenario given the scenario of well shuffled cards, given the scenario of well shuffled cards, right? There are 52 possible outcomes. Okay, so just to contrast this to, say, a die roll or a coin toss, If it's a coin toss, we have what, two possible outcomes because you could have a head or a tail. If it's a die roll, we can have six possible outcomes because your outcome could either be a 1, a 2, a 3, a 4, a 5, a 6, and that's it. So in the same way, if we take a standard deck of cards, there are 52 possible outcomes because there are 52 cards in a single deck. All right, so that's the total possible outcomes that comprise all the various types of cards you could end up selecting. So A. All right, so we can say that we can argue this way. So the cardinality, okay, the cardinality of the event queens. And here, of course, I could have represented this by some A or a Q, all right, but I just want to use the full label. So the cardinality of queens, where queens is an event. In a standard deck of cards containing 52 cards, the number of elements that are queens is 4. All right. Hence, based on the previous equation, right, we know we need the number of elements in the A. All right. We need the number of elements in the A multiplying 1 over the number of elements in the sample space. All right. Now, keep in mind that this is the same as this expression, the NA is the same as, right, so the cardinality of A. Okay, multiplying all right. So hence by this, the probability of a queen is 4 multiplying 1 on 52, which is 4 on 52, which is 1 on 26. That's 2 on 26, which is 1 on 13. That's the probability. B. We can also say that the number of fives, okay, the event 5, or if you like, the cardinality of the event 5. Keep in mind, this expression is different from saying the absolute value of 5, okay? So the cardinality of the event 5, there are 4 of them, okay? Hence, the probability that the randomly picked card is a 5 is similarly 4 by 52, which is 1 on 13. C, number of spades in a standard deck of cards. There are 13 of them. Hence, the prob of 13, the prob of spades. The prob of spades is equal to 13. All right, 13 multiplying 1 on 15, or 1 on 52. All right, and this is equal to 1 on 4. All right, and D. When it comes to the picture cards, and these are all events, right? That's why I'm writing them as number of events or cardinality of events. You could also denote them by particular letters, uppercase letters, because we know that that's how we denote events. So instead of saying maybe spades, you can say let B represents the event of spades, or let P represents the event of picture cards. So that instead of writing the number of picture cards, you would write the N of P. All right, so N of picture cards is 12 in a standard deck. All right, hence the prob of picture cards is 12 on 1 on 52. Which is 3 on 13. Okay, so let's take this other problem. So example, is our first example. Let's take example 2. So this time around, a pair of dice is rolled. A pair of dice is rolled once. Okay, sometimes we can formulate the experiment by rolling the dice twice, 3 times, 10 times, or some general n times. So a pair of dice is rolled one time. So once, okay, find the probability of observing a sum of 7, b a sum of 7 or 11, and then c a double. Okay. So here, let's understand the question very well. We have a pair of dice. So meaning we have what, two dice in our palms, not just one, but two. So it's dice, and we're rolling them one time. So we want to find the probability that the outcome, or in this case, the outcomes, because we're talking about two. So the outcomes of the two, when you sum them up, what's the probability that we're getting a 7? What's the probability that we're getting a 7 or 11? What's the probability that we're getting a double? All right. So the first thing that we need to figure out is what is the sample space of this particular experiment, right? How will the sample space look like if we have a die or a pair of dice and we're rolling this one time? How will the sample space look like? So a good way to appreciate that is this. We might have to draw, we might have to just have a visual representation so that we can determine the collection of our samples of our omega. All right. So let's say that, and this is the first bit we always need to figure out. So we can say that let's let the pair of integers I, j, okay, such that one is less than or equal to I and j, and I and j are also less than or equal to what, 6, represents. So let that I and j, that satisfies this requirement. Let that represent the numbers the numbers that appear on die 1 and die 2, respectively. Okay, so this is the setup, right? I've created this pair of I and J. I simply means the number that appears on die one, and J means the number that appears on die two. Okay, so for example, if I have a, a collection or a reference like this means that at this particular point in time, I am observing, after performing the experiment, I observed a three. Number three appeared on die one, and number five appeared on die two. All right. In order that we may not miss any pair, because now we want to enumerate, we want to list or unpack all the members within our sample space, the omega. So to ensure that we don't miss any pair, it's important that we fix the number that appears on the face of one of the dice while varying the number on the other side. So what that means is the approach is if I assume that on die one, I am observing one, as in the number one. What are the possibilities? I can get number one appearing on die one, and then number one appearing on die two. I can get number one appearing on die one, and then number two appearing on die two. I can get number one appearing on die one, number three appearing on die two, and so on and so forth. So you realize that at any point in time, to ensure that we have the full complement of our sample space, we can hold one observation constant and then vary the observation on the next or on the second die. Once we exhaust it from 1 to 6, then we switch the value on the first die. We hold it constant, we vary the second die observations, and we go through till we exhaust I and J, moving from 1 to 6. All right. So we can say that so the members of our sample space, which is essentially all possible pairs. All right. So the members of our sample space, let me put this in parentheses. So here, the membership of the sample space are not just single values, they are pairs of values. Okay. Because the sample space is the function of the experiment. The experiment here is you're rolling two dice one time. So it will not be correct to say that your sample space contains 1, 2, 3, 4, 5. No. If we had just one die and we're rolling it once, then yes, your sample space will be 1, 2, 3, 4, 5, 6. But here you have two dice. You could even have three dice and you're tossing them. So in that case, your sample space will constitute triples. If you have four dice, every member of your sample space will be a quadruple, and so on and so forth. Okay. So the members of the omega, the sample space, are basically composed of all possible pairs. All right. Okay, so the members of the omega, constituting all possible pairs, are presented as follows. So we need to create a table. Let me call this part die one. So and then let me call the side die 2. All right. So what are the possibilities here? If on die 1, I observe 1. On die 2, I can also observe what? 1. So 1, 1. Sorry, let me do this correctly. So on die 1, if I observe 1, it could happen that I'll keep observing 1, but on die 2, the values may change. So I'll have this. One, 5. Okay, so if on die 1, a 1 just appears throughout, but die 2, there are variabilities. These are the possible observations, or these are the possible pair observations. Right, so we're saying that we have die 1, and then die 2, right? So we could have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Okay. Then we could also have 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. We could have the same thing. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. And we could have 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. Then we could have die 1 can show up a 5, and then die 2 is a 1. Die 1 can show up a 5, die 2 is a 2. Die 1 can show up a 5. Die 3 is a 3, in that order. And then finally, we can have die 1 showing up as 6. And then 1. All right, so what does this mean here? This simply means that so these are all the members of your omega, all right? So thus there are how many? There are 6 by 6, which is what, 36. So there are 36 sample points or points in the sample. But you know what sample points are? Essentially elements within the sample space, the omega. So there are 36 of them by just counting. So there are 36 sample points, meaning that the cardinality of our sample space is what, 36. So in other words, there are 36 possible outcomes, whatever they are. So the first problem, A, we're supposed to find the probability of rolling what, a sum of 7. So the question we need to ask ourselves is, in how many different ways can we obtain a sum of 7? So we need to go back into the omega, right? What are the possibilities for obtaining a sum of 7? If you take a look at it closely, to obtain the sum of 7 falls on this diagonal, okay, from the left to the right. So we can get it. We can get a sum of 7 from, you see, 1, 6, 2, 5,
2, 5.
4, 3, 5, 2, and then 6, 1. Okay, so on that diagonal. So we'll say that there are
1, 2, 3, 5, 6.
so there are 6 ways of observing a sum of 7 as follows. So I'll just list them out. I could have just encircled them, but let's just list them out. So in fact, we could create a table, an event. We could create an event so a sum of 7 is made up of 6 pairs. So 1, 6, 3, 4, 4, 3, 5, 2, and then 6, 1. All right. So the probability of a sum of 7 is what? There are 6 of them. Going into each member of the sample space has a probability of what? 1 over 36. So this is what one set. The second problem is a sum of 7 or 11. All right, a sum of 7 or 11. So here there are so now the event itself. Keep in mind here we have what? A sum of 7 or a sum of 11. So it's a larger set, right? So because they will be taking unions of sum of 7 and then sum of 11. So sum of we have 1, 6, 2, 5, 3, 4, 4, 3. So it's going to be the same elements as we had, the same members as 7. We just have to add on those that sum up to 11. So 4, 3, 5, 2, 6, 1. I'm done with the 7s. Now I need to look at 11. 11, we can get it from 6, 5, and then 5, 6. All right. So how many members are there? What's the cardinality of this set? 1, 2, 3, 4, 5, 6, 7, 8. All right. Thus, and so the probability of getting a sum of 7 or 11 is 8 multiplying the probability of each element in omega. All right, 8 on 36 is 4 on 13. Then C, we're interested in the probability of a double. A double here means having the same observation on die one as die two. So if you get a die one, if you get one on die one, you're also getting one on die two. If you get three on die one, you're getting three on die two. If you get six on die one, you're getting six on die two as well. All right. So for IJ, what will be the number of ways of hitting a double? It's just going to be the single variable case, 1, 2, 3, 4, 5, 6. And then on the other hand, 1, 2, 3, 4, 5, 6. So they would end up being the pair of identicals. Okay, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. Those are the only possible ways to get a double. So let's define the event first of all. So double. The collection of doubles, we have 1, 1, 2, 2, 3, 3, 4, 4.
So the 4/13
Yes.
Is 2/9. Because if you take 2 times 36, 2 times 13, it will not give you 36. So
Oh, it's
4
supposed to be
enter
18.
enter into 36.
Yeah, sure.
Yes.
That's correct.
So
it's 4 on 18, which is 2 on 9, right?
yes.
Sure. That's correct. Yeah. So let me just yeah, thank you. That was just an oversight. So 2 on 9. Okay. Then we have 6, 6. I'm hoping that you can see the squeeze here. So here, what's the number of elements? So number of members in a double is what? 1, 2, 3, 4, 5, 6. Okay.
Sir,
Hence, the probability.
sir,
Yes,
please, you didn't add a 6, 6
I did. Yes, it's there.
to the double.
Yes, we have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. The 6, 6 is at the
Okay.
far end.
Okay, so I've seen it.
So this is the probability of a double. Okay, so this is 6 going into 1 on 36, which is 1 on 6. All right. Just to kind of make the side clearer, let me rewrite it properly. So 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6.